calculations that said, hey, the universe should be in a state of expansion, the space-time should be stretching out. He didn't like that. He liked the steady state theory, so what he did is he stuck an extra term into the calculations to offset the expansion that his own theory predicted. And he called that the cosmological constant. And we'll come back to that later. It ends up that for reasons which I'll point out in a few minutes, Einstein ended up a few years later reversing that, and he claimed it was the biggest blunder of his career because he allowed his philosophical problems with what his theory was saying to trump good science. And it ends up his original calculations were correct. Now, when you think about expanding space-time of our universe, as I mentioned here, think about it like you have this balloon and you have all these dots on the balloon. Each one of these dots, say, represents a cluster of galaxies, for example. Okay? And as the space-time expands, these things are going to get further and further away from each other. Now, it's important to understand in this analogy, this is a big misconception people have. In this analogy, it's very important to understand that the universe, the observable universe, the space-time in which we exist, is not on the inside of the balloon. It's the surface of the balloon. Okay? The surface of the balloon is the space-time of our universe. And so people always ask, oh, what's out here? What's in here? I don't know. This is just an analogy, right? We can't visualize, it's very difficult to visualize it any other way. Now, let me point something else out about the expanding space-time. Over here on the right-hand side of the picture, this requires a little bit of translation. See these two little green dots right here? Okay. I don't know if you guys can see this. Did that come out? Yes? Yes. Okay. And you see the red circles around. Okay. Now, the idea here is that as time goes on, right, if Einstein's predictions were correct, his original predictions, as time goes on, space-time expands. So let's imagine that each of these black dots is like a galaxy. Okay? And as time goes on, these are like frames of a movie, they stretch and get further and further apart from each other because they're carried by the expanding space-time. Okay? Now, these red circles represent the light emitted by those galaxies from the inception of the universe. Okay? So, as time goes on, the galaxies move further apart from each other. The light emitted by them expands, right? So if we talk about these two green galaxies that are highlighted right here and here, if we live on this galaxy, we're not going to see that galaxy until its light gets to us. Does that make sense? So in this picture right here, we haven't seen this other galaxy yet, and they haven't seen us yet. As time goes on, space-time spreads more, galaxies get further apart, still haven't seen each other. It's not until you get to this point down here in this last frame where the light from this distant galaxy actually gets to us that we finally see it, and vice versa, right? That's exactly what I was talking about before when I talked about the idea of the observable universe. So in this picture, if this is us, our observable universe is what we see inside of here. This stuff out here, we haven't seen yet because its light hasn't gotten to us yet. And the entire time, the space-time is expanding. So you remember when we talked about the idea, if the universe is 14 billion years old, approximately, and how can we say that our universe is approximately 90 billion light years across, right, our observable universe? The reason why is because of this. We can only see what's inside of here. The stuff that started out close to us has gotten substantially further away by the time that light gets to us. Does that kind of make sense? Okay, it's